Hi folks, how y'all doing? We're covering section 4.3 today, which is diagonalization. Let's go ahead and get started. So, number one says to find a diagonal matrix which is similar to this matrix A. We talked last time about what it means for two matrices to be similar. It means that the matrices do the same geometric transformation, but on two different bases. And so let's work through this. First thing we're going to need to find is the eigenvalues and the eigenvectors for A. So let's do the eigenvalues first. So we'll subtract lambda from the diagonal. And calculate that determinant. And set the determinant equal to 0. We can just do that here. So the determinant is 4 minus lambda times 3 minus lambda minus 2, which is lambda squared minus 7 lambda plus 12 minus 2 equals 0. And that factors into lambda minus 2, lambda minus 5. And so those are our eigenvalues, 2 and 5. All right. So now we need to find the eigenvectors. So when lambda is equal to 2, 4 minus 2 is 2. 3 minus 2 is 1. And so that's just the equation 2x plus y equals 0. If I set x equal to 1, then 2 plus y is 0, so y would be negative 2. And so there's our first eigenvector. Then when lambda is equal to 5, 4 minus 5 is negative 1. And 3 minus 5 is negative 2. That's the equation negative x plus y is equal to 0. The bottom row is just negative 2 times the top row. So if x is 1, then negative 1 plus 1 is equal to 0, so y is also 1. And that's our second eigenvector. All right. So let's call these eigenvectors, let's call this one B1 for the first basis vector and B2 for the second basis vector. And let's draw a diagram to show what's going on here. All right. Okay. So our first basis vector is 1, negative 2, which is right here. That's B1. But the transform version of B1 would be 2 times bigger. This is a vector, because it's an eigenvector, it doesn't rotate, it only changes magnitude. And it changes magnitude by a factor of 2. So this is the transform version of B1. And now let's look at B2. B2 is 1 unit in the x direction and 1 unit in the y direction. And the transform version of B2 would be 5 times bigger, be the vector 5, 5, which is way up here. I didn't draw that very well. Try this again. There we go. All right. And so this is what's happening in the alternate basis B. So let's see what happens in the standard basis S. We would like to find a transformation that does the same thing geometrically to the standard basis, which means that we want to take the vector E1, and the transformed version of E1 should be double that vector. So the transformed version of E1 should be 2 times E1. And then the vector E2 should be the transformed version of E2 should be 5 times E2, which is going to be, somewhere up here. And so that is, this transformation looks like this transformation, but rotated back onto the X and Y axes. That's going to be sort of the idea here. But we know what the coordinates of this matrix are. The diagonal matrix that we're looking for, the transformed version of E1 is the vector 2, 0. And the transformed version of E2 is the vector 0, 5. And so our answer is 2, 0, 0, 5. But a shortcut for this is just that the entries on the diagonal are the eigenvalues. The first eigenvalue goes on the first place, and the second eigenvalue here goes here. And so your question might be, at this stage, would it have been possible, what if I had factored this into lambda minus 5, lambda minus 2, instead of lambda minus 2, lambda minus 5? What about this matrix, 5, 0, 0, 2? Well, that answer is also correct. The requirement is that eigenvalues have to appear on the diagonal, but they can appear in either order. And so if you factored this in a different order, that doesn't change whether you're right or wrong. That's also a correct answer. Okay. In the example 2, we're going to continue to work with this matrix, 4, 1, 2, 3. And so all of this information is going to be useful in example 2 as well. All right, let's move on. So the diagonalization of a square matrix is the relationship A equals PD P inverse, where D is a similar diagonal matrix and P is the change of coordinates matrix. Write the diagonalization of this matrix. Now, from example 1, we know that the eigenvalues are 2 with the eigenvector 1, negative 2, and 5 with the eigenvector 1, 1. And so we know that the diagonal matrix is 2, 0, 0, 5. The change of coordinates matrix is 1, negative 2 in the first column and 1, 1 in the second column. It has the eigenvectors in the columns. So the D matrix contains the eigenvalues. The P matrix contains the eigenvectors. So in the last slide, I said that the order of the eigenvalues didn't matter, that we could have also done the matrix 5, 0, 0, 2. But if we do that, then the eigenvector for 5 is 1, 1. That becomes our first eigenvector. And the eigenvector for B2, for lambda equals 2, becomes our second eigenvector. That is, the order that we put the eigenvalues doesn't matter, but the eigenvectors have to match the order that we've chosen for the eigenvectors. So either order is fine, but you have to be consistent. When 2 goes into left column, then 1, negative 2 goes into left column. When 5 goes into left column, then 1, 1 also goes into left column. Okay? So the order doesn't matter as long as you are consistent about it. But there's a third part to the diagonalization, that's calculating the inverse of P. So that's 1 over the diagonal of, not the diagonal, the determinant of P. That's 1 minus negative 2 is 3. And then the main diagonal switches positions. The other diagonal switches signs. And so that's that matrix 1/3, negative 1/3, 2/3, and 1/3. And when we put all of this information together, the diagonalization is the, that's not what I wanted to do, sorry. I wanted to turn that off so that we can see what I'm writing here. There we go. The diagonalization is the matrix A, which is 4, 1, 2, 3, is equal to P times D times P inverse. 1, 1, negative 2, 1 is our P. D is 2, 0, 0, 5. And P inverse is 1/3, negative 1/3, 2/3, and 1/3. I will also finish up this other version of the answer, just so you can see what happens. The determinant of this P matrix is negative 2 minus 1, which is negative 3. Then we switch the negative 2 and the 1, and we change the signs for the other values. So we have a lot of negative signs, but this negative sign in the determinant will cancel out with most of them. And that's going to give us a 2/3, 1/3, 1/3, and negative 1/3. Okay? And therefore, A is 4, 1, 2, 3, but it's also equal to P times D times P inverse. So that would be 1, 1, 1, negative 2 times 5, 0, 0, 2 times 2/3, 1/3, 1/3, and negative 1/3. And again, both of these answers are correct. All right. So that's how we diagonalize a square matrix. We find the eigenvalues, those go into D. We find the eigenvectors, those go into P. Then we also have an inverse to calculate. And we string those together and get a diagonalization. All right, so let's move on. Here we have a 3 by 3 matrix. We would like to determine the diagonalization of this 3 by 3 matrix. All right, so it's going to take us a little bit longer because it's a bigger matrix. The eigenvalues, we're going to take the determinant of 2 minus lambda, 0, 0, 1, 2 minus lambda, negative 1, 1, 3, negative 2 minus lambda. And set that equal to 0. Since there are a bunch of zeros in the top row, I'm going to do a cofactor expansion along the top row. And we're going to get 2 minus lambda times the cofactor in the 1, 1 position is equal to 0. But that is the determinant of just this matrix. All right, and that determinant is 2 minus lambda times negative 2 minus lambda plus 3. So here we get lambda squared minus 4 plus 3 is lambda squared minus 1. And that factors into lambda plus 1 and lambda minus 1. And so we get 3 answers. Lambda equals 2, lambda equals negative 1, and lambda equals positive 1. We have 3 eigenvalues this time. All right. So now we're going to find the eigenvectors. Let's give this a try. All right. When lambda equals 2, 2 minus 2 is 0, so the top row becomes all zeros. 1, 2 minus 2 is 0. And negative 2 minus 2 is negative 4. This time we're going to have to do a little bit of row reduction here. I'm going to bring the 1, 0, negative 1 to the top row. And take this row and subtract that. So 1 minus 1 is 0. 3 minus 0 is still 3. Negative 4 minus negative 1 is negative 3, 0. And the bottom row is all going to stay the same. Or the bottom row actually is the original top row. It's all zeros. And so what we have is x minus z is 0. And if I divide this by 3, I get y minus z is equal to 0. And z is free. So if we set z equal to 1, 1, 1, 1 is our first eigenvector. All right. So then let's try lambda equals negative 1. Let's see what happens here. 2 minus negative 1 is 3. 2 minus negative 1 is also 3 here. And negative 2 minus negative 1 is negative 1. All right. So let's do a little bit of row reduction. The top row will divide by 3 and just gives us 1, 0, 0, 0. The middle row, if we just cancel out that 1, we get 0, 3, negative 1, 0. And the bottom row is the same as the middle row, so it goes away. And so we're getting this time that x is equal to 0, but 3y minus z is equal to 0. So if I set y equal to 1, 3 times 1 minus 3 is equal to 0. So 0, 1, 3 is our second eigenvector. All right, one more. Lambda equals positive 1. So 2 minus 1 is 1. 2 minus 1 was 1 again. And negative 2 minus 1 is negative 3. All right. I'm going to do quite a bit of row reduction here. I'm not going to write it all out because I'm out of space. But I'm going to cancel row 1 from row 2 and row 3. That is, I'm going to go ahead and change these ones to zeros. And since 1, negative 1, and 3, negative 3 are multiples of each other, I'll also cancel the entries in row 3 using row 2. And that tells me that x is 0, but y minus z equals 0. And so 0, 1, 1 is our third eigenvector. All right. So now we know that our diagonal matrix is 2, negative 1, 1 on the diagonal and zeros everywhere else. And then our P matrix is, our first column is 1, 1, 1. Our second column is 0, 1, 3. And our third column is 0, 1, 1. We have to find the inverse of that, though. And that's going to take some row reduction here. So we'll augment this with the identity matrix. And we'll cancel the ones here. So we'll do row 2 minus row 1 and row 3 minus row 1. Zero, 1, 1, negative 1, 1, 0 for the second row. 0, 3, 1, and negative 1, 0, 1 for the third row. All right. Then we'll cancel this 3 with row 3 minus 3 row 2. Zero, 3 minus 3 is 0. 1 minus 3 is negative 2. Negative 1 minus 3. Negative 1 minus negative 3 is positive 2. There we go. 0 minus 3 is negative 3. And 1 minus 0 is still 1. All right, 2 more steps. Row 3, we're going to have to divide that by negative 2. Zero, 0, 1. 2 divided by negative 2 is negative 1. Negative 3 divided by negative 2 is positive 3 halves. And 1 divided by negative 2 is negative 1 half. So we're getting some fractions there, but that's okay. And the last thing we have to do is clear out this 1. Row 2 minus row 3. So 1 minus 1 is 0. Negative 1 minus negative 1 is also 0. 1 minus 3 halves is negative 1 half. And 0 minus negative 1 half is positive 1 half. And so this is our inverse matrix. We have the identity on this side, so the other side is P inverse. We don't have a lot of room to write our final answer, but we can fit it in right up here. A is 2, 0, 0, 1, 2, -1, 1, 3, -2, and that equals to P, which is 1, 0, 0, 1, 1, 1, 1, 3, 1, times D, which is 2, 0, 0, 0, -1, 0, 0, 0, 1, times P inverse, which is 1, 0, 0, 0, -1/2, +1/2, -1, 3/2, and -1/2. And that is the diagonalization of the matrix A. So we can do a 3x3 matrix. It just takes a little bit more work to wrangle all of that information, but we can do this. Let's keep going. I'll give you a second to write things down. If you need to, pause the video. There's a lot of information on this slide. All right. Why is this identity true? That if I raise a matrix to the k power, I only have to raise the middle matrix to the k power. And I don't have to raise the p and the p inverse to the k power. We have diagonalized, and we know this is true. So if we do a squared, that should be the whole thing squared. And it is, this is correct. But if we write that out, that's PD P inverse times P times D times P inverse. And these two matrices are inverses of each other, and so they cancel. And so this gives us P times D times T times P inverse, which is just P times D squared times P inverse. And if we keep going, A cubed is PD P inverse cubed, which is PDP inverse times PDP inverse times PDP inverse. But these two matrices cancel, and these two matrices cancel. And so we get P times D times D times D times P inverse, which is just P times D cubed times P inverse. And so a side effect of diagonalization is that if we want to raise a matrix to a power, we don't have to worry about taking P and P inverse to a power. We only have to worry about the diagonal matrix. And that will save us a little bit of time here. All right. So let's use that information here. I have this matrix here, 7, 4, -12, 7, and we want to raise this entire matrix to the 500 power. I think the result may surprise you. Let's give this a try. Okay. So we know from the information that we're given that the diagonal matrix looks like 1, 0, 0, -1. The P matrix is, let's see, 2, 3. That eigenvector goes with 1, and this eigenvector goes with -1. So then let's look at P inverse. That's going to be 1 over the determinant. 4 minus 3 is 1, so the determinant is just 1 in this case. The 2's switch places. The 1 and the 3 switch signs. So that's just 2, -1, -3, +2. And so A is P times D times P inverse, which is, let's see. P is 2, 1, 3, 2. D is 1, 0, 0, negative 1. P inverse is 2, negative 1, negative 3, 2. So a to the 500 power is P doesn't have to be raised to a power. D does have to be raised to the 500 power. But we've got a special case here. The E vector doesn't change. E1 vector, sorry. The transformed version of E1 stays the same. And so if I have a transformation that doesn't do anything to E1, and we do that transformation 500 times, it still won't do anything to E1. The transformed version of E1, even after 500 transformations, is still going to be 1, 0 because nothing happens to E1. So let's talk about what happens to E2. E2 flips around the horizontal axis here. That is, E2 is the vector 0, 1, and when we transform it, it just flips downwards. The transformed version of E2 is 0, negative 1. But if all the transformation does to E2 is it flips the position, then if we transform it again, it will flip back into its original position. And then if we transform it again, it'll flip back downwards. And every odd flip will flip it downwards. And every even flip will flip it upwards. That is, it's like an even number raised, or sorry, a negative number raised to an even power becomes positive. And so we're flipping E2, but when we flip it 500 times, that's an even number, and it ends up back in the original position that we start with. So when we do this transformation 500 times, we get the identity matrix here. And multiplying by the identity matrix doesn't do anything. And so we get 2, 1, 3, 2 times 2, negative 1, negative 3, 2. But that's P times P inverse. And P times P inverse is the identity matrix. It may surprise you, but if we do this matrix 500 times, the result is that E1 ends up back in its original place, and E2 ends up back in its original place. A to the 500 is equal to 1, 0, 0, 1. All right, let's move on. When is a matrix not diagonalizable? Are there cases when we can't do this? And the answer is yes. A matrix is not diagonalizable if there are not enough eigenvectors to form a square matrix. So in the next example, we're going to see a non-diagonalizable matrix. Okay, so let's try this one here. This matrix is not diagonalizable. We're going to determine the eigenvalues and the eigenvectors of A and explain why not. So here's what's happening. If we go to the eigenvalues, we want to take the determinant of 2 minus lambda, 1, 0, and 2 minus lambda. and set that equal to 0. But this determinant is 2 minus lambda times 2 minus lambda minus 0, because the other diagonal is 0. And we only get one eigenvalue. Lambda is equal to 2. Now there's some fancy language they use in a book, is because this is a repeated root, because lambda equals 2 is actually a double root of this equation, we say that lambda equals 2 has an algebraic multiplicity of 2. It doesn't matter to me whether you use that language or not, but even though we have a 2 by 2 matrix, we only have one eigenvector here. Oh, one eigenvalue, sorry. So when we go to find the eigenvectors, well, let's give that a try. We only have one eigenvalue to work with. When I subtract 2 from the diagonal, I get 0, 1, 0, 0. And that's just the equation that y is equal to 0. So y has to be 0. X can't also be 0 because an eigenvector has to be a non-zero vector, but x can be 1. X is a free variable. There is no pivot in the x column, so x can be anything. We can set x equal to 1. But I only have one eigenvector. And therefore, I don't have enough eigenvectors to form a square matrix. Again, some fancy terminology. If we see this in the book, lambda equals 2 has a geometric multiplicity of 1. Algebraic multiplicity is how many times does this eigenvector show up when we factor the determinant. Geometric multiplicity is how many eigenvectors do we get out of that set of equations. If there were two free variables, we might have something that looks like s times a vector plus t times a vector, and we might have two eigenvectors, and then we would have a geometric multiplicity of 2. But in this example, we just have a geometric multiplicity of 1. There's only one eigenvector. So we don't have enough eigenvectors for a square matrix. So we can't form P and P inverse. Now, as a little sidebar here, you may be thinking, if x is a free variable, then why can't we just pick two different values for x? Let x be 1 and let x be 2, for example. 1, 0 is an eigenvector, and then 2, 0 is also an eigenvector. And why can't we let that be our p? And the reason is that because these columns are multiples of each other, the inverse won't exist. If we try to find the inverse, we would take 1 over the determinant, but the determinant is 0 minus 0, and that's not allowed. We can't take the determinant, the inverse. And therefore, it's still not diagonalizable because we still can't form a P inverse. And so when you have a free variable, you can't just pick two different things for the free variable and hope it works, because you just get two different multiples of the same vector. And so That's why we don't have enough information to form square matrices for P inverse, P and P inverse. Okay? So this matrix cannot be diagonalized. All right. Let's try this with a 3 by 3 matrix real quick. Just so you can see an example of slightly more complicated example of how multiplicities come into play here. So in this example, I'd like to find the eigenvalues first. And that will be the determinant of, we're going to set the determinant of 1 minus lambda 1, 0, 0, 1 minus lambda 1, 0, 0, 2 minus lambda. Set that determinant equal to 0. This is already in echelon form. And so the determinant is what we get when we multiply down the diagonal. And so lambda is equal to 1, lambda is equal to 1 again, lambda is equal to 2. So we really only have 2 eigenvalues. But lambda equals 1 has what they call an algebraic multiplicity of 2. All right. So now we will find the eigenvectors. All right. See what happens here. Let's start with the eigenvalue that doesn't have the multiplicity. Let's start with that one. So when we plug in lambda equals 2, 1 minus 2 is negative 1. 1 minus 2 is negative 1 again. And 2 minus 2 is 0. All right. I'm going to do negative of row 1. That's going to get me 1, negative 1, 0. 0, negative 1, 0. Sorry, this should be a 1 here. Let me fix that. I have lost my pen. There we go. That should be a 1. That should be a 0. This should be a 1. And there we go. All right. Actually, let's go ahead and take the negative row 2 also. That'll make this a positive 1 and a negative row 1. And then we'll take row 1 minus row 2, and we get 1, 0, 1, 0, and 0, 1, negative 1, 0, and 0, 0, 0, 0. And so z is our free variable. X plus z is equal to 0, and y minus z is equal to 0. And so if z is 1, y is 1, but x is negative 1. And so we have an eigenvector there. Let's look at lambda equals 1 here. 1 minus 1 is 0. 1 minus 1 is 0 again. And 2 minus 1 is, 2 minus 1 is 1. And then if we just do row 3 minus row 2, we get 0, 1, 0, 0, 0, 1, 0, 0, 0. This time, X is free, but Y has to be 0. That's what this equation says. And Z has to be 0. And so if Y and Z have to be 0, but X is free, we can set X equal to 1, but we only have one possibility. We can take multiples of this eigenvector, but multiples don't make the matrix invertible. And so lambda equals 1 has a geometric multiplicity of 1. It only has one eigenvector. And since I have 2 eigenvectors but 3 rows, I don't have enough information for a square matrix. And so this is another example of a matrix that cannot be diagonalized. All right. So recapping, we have seen how to diagonalize a matrix. We have done an example of diagonalizing a 3 by 3 matrix. We've used the diagonalization to raise a matrix to a large power. And we've seen some examples of matrices that cannot be diagonalized because we have a repeated eigenvalue that doesn't have enough eigenvectors to match up with the repetitions. All right. Let's wrap up. Take care. I'll see you around next time.